Good morning, chemistry students. Let's talk about dynamic equilibrium. These are 11.1 notes, and what we want to look at is what does this word equilibrium mean, and especially in terms of chemical reactions. So if we want to define equilibrium, what we're saying is the forward and reverse reactions are occurring at equal rates such that it looks like the conditions remain the same. So what does that mean? Well, you've seen reactions now that have this double-sided arrow. That means that there's two reactions that we can look at here. The reaction where hydrogen and iodine form hydroiodic acid, and also what we call the reverse reaction, where our hydroiodic acid breaks down or decomposes into hydrogen gas and iodine. And so instead of writing both of these, what we do is we use the reversible arrow to indicate that both of those reactions are capable of occurring. And so when these reactions are at equilibrium, what that means is that the forward reaction, or what we call the arrow, when you read it from left to right, our conventional way of reading it, that's happening at the same rate as our reverse reaction, reading it from right to left, or the second reaction that I wrote. What ends up happening is that our conditions remain the same. So however much reactant and product you have is how much you retain, because every time you form more product, the reverse reaction occurs and you form more reactants again. Now, this doesn't mean that you have equal amounts of reactant and product. Just the amounts you have don't appear to change. And so we can graph this. If we look at our graph, on the x-axis, we have time moving forward. On the y-axis, we have our reaction rate. So as time moves on, we are going through the reverse reaction, and we are going through the forward reaction until we hit equilibrium. So let's look at a specific example of this, one that you're probably aware of, and that is rechargeable batteries, like the batteries you can purchase or the batteries in your phone. So you plug in your phone and you recharge it. So one example of this reaction is this. So in this reaction, we have lead and lead oxide and sulfuric acid forming in a reversible reaction, lead sulfate and water and energy. So the forward reaction, reading from left to right, is the reaction that releases energy. So when you're using your phone, your battery is releasing energy to power the phone. When you plug your phone in and you put energy into your phone, that energy causes the water and the lead sulfate to react to form lead and lead oxide and sulfuric acid, which is what recharges your phone. You're remaking these reactants so that when you unplug it, you can form energy again from the battery to power your phone. So it's a really important reversible reaction, the one that makes energy and then takes energy to allow you to recharge that battery. So what we're looking at is our reactants combined to make a product. Our products can break apart to reform the reactants. That's the basis of a reversible reaction, is we can use reactants to form products, and those products can break back down into the reactants. And so we're able to cycle back and forth between these two. So what we want to do then is, now that we know that reactions are reversible and that they can have an equilibrium, or in other words, the rate of the forward reaction, the rate of making products, can be equal to the rate of remaking those reactants, we want to express that as a constant. So if we take some sample reaction, A plus B yields in a reversible reaction C and D, and we'll represent their coefficients with the letters N, M, X, and Y. So those are our placeholders. Well, our general formula the equilibrium constant is this. KEQ, or the equilibrium constant K, is equal to the concentration, remember brackets mean concentration of the products, over the concentration of the reactants raised to their coefficients. So for our sample reaction, KEQ would look like this. The product C raised to its coefficient X times the concentration of product D raised to its coefficient Y divided by the concentration of reactant A raised to its coefficient N times reactant B's concentration raised to its coefficient M. Some things to note when you write this is if any of your reactants or products are solids or liquids, we do not include them because they do not significantly change our equilibrium constant. So in other words, this is gas and aqueous only. Equilibrium constants are temperature dependent. So we have to know what the temperature is, and that's going to play a role in this. And our answer is a unit free number, just like pH. So it's representative and it is unit free. So when we get an answer for the equilibrium constant, what does that mean? Well, if you get an equilibrium of 1, that tells us that the product concentration is equal to the reactant concentration. So they actually are, they're not only in equilibrium, which means their rates are the same, but the amount we have is the same. If you get a very large value for your equilibrium constant, something greater than 1, that tells you that you have more products than you have reactants. So we're favoring the products, or in other words, the concentration of products is greater, or the equilibrium is favoring the making of products. So even though we're doing both reactions, the forward, making products, and the reverse, making reactants, there's much more product. If you get a very small number for your equilibrium constant, something less than 1, that tells you that you are favoring the reactants. There are more reactants than products, or what we call a stronger reverse reaction. We're going to continue to make more sense of this idea of what it means to favor the forward or favor the reverse reaction. So let's go ahead and practice these. I'm going to do the first example for you, then I'll ask you to pause and try the second example yourself. All right, so in our first example, we have hydrogen gas and bromine liquid in a reversible reaction to form hydrobromic acid as a gas. All right, so our equilibrium constant is equal to the concentration of the products raised to its coefficient over the concentration of the reactants raised to their coefficient, but then we know that solids and liquids do not significantly affect our equilibrium constant. So we're going to not include anything that is a solid or a liquid. So our equilibrium constant for this reaction is HBr concentration squared over hydrogen's concentration. And since we have nothing to plug in, this is our answer. This is the representation of the equilibrium constant. Go ahead and pause the video and try and write the equilibrium constant for the next reaction of ammonia and oxygen forming nitrogen monoxide and water. Okay, hopefully you've had a chance to try that. Let's go ahead and go over the answer. The equilibrium constant is equal to the concentration of the products raised to their coefficient. Water's a liquid, so we're going to leave it out, over the concentration of the reactants raised to their coefficients. And there we go. That is our equilibrium expression. So when we want the expression, we're looking for almost like writing a formula, something we could eventually plug into if we know the concentrations. So for our last example, let's go ahead and do that. Let's write the equilibrium expression, and then we'll be given information on the concentrations, and we can go ahead and solve. All right, so here's our last example. Oxygen gas and hydrogen gas in a reversible reaction to make water. Go ahead and pause the video and try and write the equilibrium expression. When you've done that, go ahead and hit play and we'll continue from there. Okay. So our equilibrium expression is equal to the products. We have no product that's a gas or aqueous. So it's just one. Everything else cancels out there or is left out over the concentration of our reactants raised to their coefficients. So there's our expression. Now we're told if all the concentrations are 0.275 molar at equilibrium, what is the equilibrium constant for this reaction? So once we've written our expression, now we can plug in 1 over the concentration of oxygen is 0.275 molar times the concentration of hydrogen, which is 0.275 molar as well, squared. All right, once we've plugged that in, then we're going to solve for this. And so order of operations, what you want to do is do 0.275 squared first, then multiplied by 0.275, then do 1 over that answer, and you should get 48.1. Remember, this is a unit-free number. And so now what we want to look at is, okay, if the equilibrium constant is equal to 1, then our products and reactants are equal to each other. This is larger than 1. Therefore, what we can conclude is that the product concentration, or the products, will be greater than the reactant concentration at equilibrium. So this lets us determine something about our concentrations when this reaction is at equilibrium. In this case, we will have more products than reactants when we hit equilibrium. Okay, go ahead and try your 11.1 worksheet and check back in with the answer key tomorrow. Have a great day, and thanks for doing chemistry.